Hey guys, and welcome back to my channel. And I have a bit of a treat for you guys. I am repairing this surface mount board, the 83970GS. You can see the part number here on the bottom, but this particular board I don't see very often, and you're going to find this on a lot of Generac boards. This board is a replacement for the through-hole component board that was very popular on a lot of these XL and EXL machines. And this was the last version that Generac, Briggs & Stratton made before they discontinued it. And a customer had sent this in to me for repair. As you can see here, it's missing the R3 voltage adjustment potentiometer here. And what we're going to do is we're going to go and fix that and then check the board for all these other components. I'm using my Tomlov 4K digital microscope so you can see this very, very clearly. And it's going to be very helpful for me as well because this thing is extremely small. What I also am going to do is I'm going to also add in this other camera angle. As we're testing the components, we can actually see what we're actually seeing on the multimeter and whatever the values are. I can flip this around and I can move this around just a little bit just so we can see what I'm doing here on the microscope. And a lot of these components are pretty much the same, just in a different format of the through-hole mount. Now we have these surface mount with these MELF diodes and some of these surface mount capacitors, these really tiny transistors. The circuit is essentially the same. Now here we have the board, a little bit a wider screen, and as I mentioned, I am going to go ahead and replace R3 here. It looks like there's a decent amount of damage here. Also, we're going to need to check R15, which shows a little bit of discoloration. And if I flip the board over, we see here that we are missing a trace that's going back over to the snubber connector here. So that right there is an issue that we're going to have to run a jumper wire to fix this trace. Now let's go ahead and check out R15. Now I know R15 to be about 12 kilo ohms, and this is always one of those resistors that burns, but it doesn't, it's meant to handle the heat. Now let me just see if I can get this to hold. All right, we are definitely getting about 12 kilo ohms, so that resistor is in good shape, even though it shows a little bit of discoloration. I'm going to call that good. The other part that I want to check now, I'm going to set my meter over to diode test. Let's see if we can show this here with the light. We're going to look at Q1. Go ahead and zoom in on that. Don't know which one is the gate, drain, and source, but I know what you're supposed to see. I can get my test leads to do this as I'm looking past the camera onto the screen here. We are getting an infinite ohm, which is good. Should see infinite ohms here on both. Okay, so there's my 1.58. That looks about right. Now, if I go ahead and switch my leads, I should see about 0.5 to 0.7 on one of these leads here. So let's try this. And there we go, 0.67. That is definitely right. Now, what if I go back over here to the other? No, I'm not getting anything there. So let me put my leads back here. There we go. So the other side of the transistor is showing 0.675. So Q1 is still good, thankfully. Normally, what I would do is Q1 and C7 are the most common failure points of this circuit here, and these would have to be replaced. Now, you could see that the sheen or the gloss of this particular board is sealed so that you can have some protection against the elements, whether it be heat or moisture. And this whole entire board is coated in that non-conductive material. And we'll have to go and be mindful of that here as well. I don't think it's going to be too big of a deal if we just clean this up here and then put in a new potentiometer on this side of the board with some hot snot glue to give it a little bit of rigidity and strength. Now, on the back of the board here, as I mentioned, we have this, let's see where we are here. Oh, wait, we got to flip it around. There we go. Yeah, we got some damage here. We're going to have to replace the trace here. And this piece is completely gone. Actually, it's probably flipped over. Where we have to get this. Yeah, it's gone. But then that leads back to this point right here. We'll definitely have to replace that. I have some small wire that we can use. And what we're going to do is use the Hako 808 desoldering gun to get these solder pads cleaned up. And then I can go ahead and install the new 10K resistor. Also notice here too, where R3 is, this trace has also broken, which leads to this part of the resistor. This is R2. So this piece needs to be jumpered back over to the potentiometer as well. And that is just yet another piece that we're going to have to fix. All right, we're on the back of the board here, and I've changed out my soldering iron tip. So what we're going to do is we're going to make a jumper wire that goes from here all the way up to this solder lug here. And once I'm done adding the wire jumper here, I'm going to put some neutral curing silicone on it so that it stays in place. I've already used my desoldering tool to take out the lugs that were stuck here where the 10K potentiometer is going to go. I'm going to go and turn off the audio and speed up the video a little bit just so you can see the process of how I do this. And this is one of the first steps in repairing the damage to this board. All right, now that we got that jumper wire fixed, I'm just going to clean up the front side of this board with some rubbing alcohol. I'll put the silicone on the back of it once I'm all done, making sure that this circuit works properly. Now we obviously have a problem here because there's no solder pad here to go and attach to, so I'm going to have to get a little creative here with how I'm going to attach this part of the resistor over to this leg of the potentiometer, which is going to be some of that off. That's better. We're not going to use that middle lug there. You can see where the trace went. You can see where the burn mark is there. But now that it's drying off, all right. Well, I actually got an idea. I'm going to try to actually get some stick-on copper trace instead of a jumper wire for this particular fix, and I think that ought to do it. All right, so what I've done is I've actually taken some copper trace that I've cut, and what we're going to do is I'll have to cut this to size exactly. And use my tweezers here to try to get this on there as straight as I can. Once it adheres, I'll make the connection. Probably made it a little bit bigger than what I needed. That's okay. Doesn't need to be pretty, it just needs to work. I'm going to go and cut that to size. Board is a little trickier to work on because of the smaller components. So grateful to have this microscope because something like this, and here's another example. I don't see if this is the piece of copper that I basically made. A little extra. I don't think that's a problem. Could be able to here where the solder pad went. There it is. Actually gives me an idea. Pull this back. Knife here. Slice it a bit. Try to neaten it up just a little bit. Just a little better on this for you guys. There we go. Excellent. Now what we'll do, add a little bit of solder to the other side of that resistor so that we have a good solid connection. There's flux already in this 6040 solder, so that should allow things to adhere nicely. Where having the smaller tip comes in handy. The other solder pad there. And I'll check all this with a multimeter here, make sure that these all have a good connection. I think that's going to work out good. All right, we're just slightly above the PCB there, and that's just so I can get that one leg of the potentiometer soldered in, and then what I'll do is I'll put some silicone on the back of this so it doesn't have any lateral flex like this here. I'm going to go ahead and solder the back side of the board, and we should be in good shape because I don't think there is, focus this a bit. One thing I didn't get was the autofocus Comlov, which is okay, but I think this one has a much better sensor. Really zoomed in a lot here. All right, so there is that one trace going to R15. So we'll just double check that trace. I didn't see any damage on that one, but we'll again check it with the multimeter when we're all done. Carefully. Trace is a little delicate. Don't get any other problems. So you could see, tweezers, that this leg and this leg are bonded together, and then we have this leg separate from it. We're only using one side of the potentiometer, so that's good. Let's try to clean up that section one more time. That's better. Now we'll go ahead and we'll solder all these pieces in. And a little bit more liberal with this one, since that's got to get flown up, flow the solder up to the top part of the board. I think looks pretty good. And now we're going to check our work. I just got my meter set to ohms, so I want to test between this point and this point. I should have continuity back here. And we do, about 3 ohms, which is good. And then finally, there is a trace that goes to here to R15. Sorry, that's out of focus, but I'm just going to double check that by connecting my pin tester over here. And beautiful. Okay. And then this pin and this pin, these two pins are bonded together, so we should be okay. It is not perfect. Off to the side a little bit, but I'm going to put some silicone cement there that should keep that from moving around, but the connection has been reestablished. Now we're going to have to go and re-secure this so that it doesn't flop around like it is here. Just going to go and do that here. That way, hold it in place like so that you don't have this flopping around. There we go. Now I'm going to use what's called hot snot. It's basically just hot glue, and this is what gives the mechanical strength. That was actually on there from the factory. This also will act as a insulator as well. That way, when he pushes back as he's adjusting the potentiometer, he'll have something to push back against. Now I put a dab of that hot glue there just to hold the wire in place, but what we're going to do is just add some of this neutral curing silicone, which should dry clear, and that will make this wire pretty secure, stuck to the board. Not going to look pretty, but it will insulate it. A little messy. Try not to waste it. The same kind of stuff I use when I'm securing capacitors to circuit boards for some of my amplifier repairs. But already I can see that this is work out okay. Just may not be the cleanliness job to do. Try to spread it around a little bit. And this silicone is very similar to the other insulating material that they have on here. And we'll go ahead and we'll cut these pins down too. I think that ought to do it. All right, we're going to go ahead and just let that silicone get set up. In the meantime, to check the Moldex connector, you can see that there are 3 pins in there. These are notorious for rotting away, and then you have to replace them. But these look in pretty good shape, although I probably will clean that up. I see a little bit of green corrosion, but if you look down the throat of the connector, you can see those pins are still in there very nice. I found that the silicone can cure a little bit quicker using some UV light. We'll go ahead and do that here for a few minutes, and that should hopefully cure it a little bit quicker than I usually wait it for. All right, and here's a test of the voltage regulation. So right now it's powered off. You need to run 120 volts to the blue wire, and then to the bottom spade connector of your voltage power regulator board here, you should see roughly 117 kilo ohms. Just make sure I get a good connection here. All right. Now, with this potentiometer turned all the way counterclockwise, you're going to see that that resistance won't change. So I'll turn on the power here. It's not going to change too much. I'll shut it off. And now I got to do this with both hands here off camera. I'm going to go and turn this completely clockwise, and we should see that number drop down to about 64 to 68 kilo ohms. All right, it's all the way clockwise. Now let's go and turn on the power. And there we go. So the voltage regulation circuit is repaired. All right, now that we know that the voltage regulation circuit is working properly, we need to then go and test the idle control circuit and then also the low oil shutdown circuit. And I thought I was home free. I didn't show this on camera, but turns out that the bridge rectifier is bad on this board. And the way I can tell is that if you see right here, these traces are completely gone. So I thought that that was just part of the ancillary failure of the voltage regulation circuit, and I jumpered the two points right here, but I should have tested in between, because once I check it here, if I can get a good connection with my leads, it's a dead short, which tells me that that bridge rectifier is bad. So I'm going to have to go and replace that bridge rectifier. So let's go ahead and do that. All right, we got the bridge rectifier removed. Thankfully, not all the traces were destroyed. You can see the hot and the neutral here. This is your AC input, and then this is your DC output on the 2 outer pins. I checked this D4 diode. You can't see it from the, there you go. It's D4. That diode is good. This jumper is okay. And I don't see any of these other MELF diodes, D10, D5, and Q2, which operates the transistor that goes up here to Q3 for the low idle solenoid control. Those are all fine. So it looks like it's just a bad bridge rectifier. And I'll go ahead and replace that. Now what we can do is right here, that is the part. And if I go and set my meter to beep at the ohms, bet you any money that this is going to show shorted. Yep. So we got ourselves a bad bridge rectifier. Let's go ahead and replace that. All right, well, I was able to get the new bridge rectifier on. I'll show that here in the next segment. I did have a little bit of trouble, actually a lot more trouble I would care not to show because I'm a little embarrassed to say, because the part was actually left over from another project. And as I am doing this jumper repair, there was very little of the original piece sticking out of the board here. So I had to sand it down, file it just to get it to fit correctly. And that was just a pain in the butt. So what I'm doing now is I'm replacing the broken trace of that board by connecting this here. Right? And this basically acts as the fusible link, to be honest, because there is no fuse in this particular circuit. So get that to stay on there correctly. And the same thing goes with this. Go ahead, carefully help the solder, which I already put some flux on it before. Okay. And these are the input AC wires. A little bit more solder here on that. There we go. Well, that's in place. Actually, probably do a little bit more solder. Definitely my fault for not putting enough solder here. This is getting very tedious. Get it on there exactly. There we go. Right. Sorry if this moved over here a little bit, but now you can see what I was trying to do. Those are in. Again, it's ugly, but it doesn't need to look good. It just needs to work. And I will definitely put some neutral curing silicone to seal that up. But now we go ahead and test for a short circuit. I don't think I'm going to find it now. As like I mentioned before, this bridge rectifier was definitely bad. We got a dead short here in the two middle. Set this over to beep. Yep. Now over here, nothing. So I think we're good. I will go ahead and button this up. Let's give this one more quick test on the idle control circuit, and then we'll just test the other components for the low oil shutdown, which is basically just the timer circuit. And that's it. I think we'll be done. This one threw me for a loop because usually I don't see these bridge rectifiers burn out. Go and set this up here. You can see it a little bit better. You can probably tell it's right up against the board. I did not have enough of these leads coming out. I think I had this for another project, but I cut them too short last time, and this is the last one that I got. Otherwise, I would have had to order it. But thankfully, none of the other traces are bad. Give it a try. All right, here we are going to go and test the idle circuit. So what we have is we have the hot connected to the white, the neutral connected to the green, and the pins 2 and 3. Pin 2 is the negative, and the green one, pin 3, is the positive. Right now we're showing in millivolts, so what we should see is about a 5 volt before it charges up. And let me just zoom out a little bit. So when I apply 120 volts to this particular circuit, it should go from 5 volts to 109 DC volts, and that's what powers the solenoid. So here it goes, power on. And it goes right to 109 because I just had it powered. All right, well, no more snap, crackle, pop, and I know for sure that that circuit is working correctly. Awesome. Well, guys, I'm just in the home stretch here, so I've added some hot snot glue here to get some strain relief on these wires here, which is what was on there from the factory. I also put a little bit around the bridge rectifier since the leads were a little short, but that should be held in by the solder points at this time. And then this is dried nicely, so you have plenty of, I'm putting a good amount of force there. Obviously, you don't want to do that when you're trying to adjust the voltage, but it's got a lot more strength than it did without having that glue behind it. The only thing I'm going to do now, and this is, I'm going to have to wait a little bit for it to dry, is these jumpers. In order to fix it from the front of the board, I'm just going to put a little bit of silicone, neutral curing silicone on those points, and once it dries, it should be safe from the elements there. And I'm going to call this done. Certainly a bit of a challenge. I'm sorry I didn't have a chance to do all of the video for some of the screw ups. I actually plugged in the idle circuit, not realizing that the bridge rectifier had failed and it had basically popped and these wires basically burned, which proved to me that yes, these are the fusible links on this particular circuit. It's only drawing about 1.6 amps. Actually, probably even a little bit less than that. I think it's 1.6 kilo ohms at 109 volts, and whatever that comes out to for current. It's very, very small, but in the event of a short circuit, those wires there are going to wind up burning off, and that caused the circuit to go open. But I think we are in good shape, guys. I've been really wanting to get this video down because I don't see these boards coming in for repair that often. You just got to be very careful when you're checking. Here, let me try to focus on it here a little better. There we go. You can see that these components are just very, very small, very hard to work with, but they're very clearly numbered. And I do have a parts list too for this surface mount version. It's, again, not often that I see it, and thankfully I have a nice example here where you can go and view all of the individual components here. And as I try to focus a little bit better, I keep moving the board here. I can actually move in just a little bit closer, give you guys a quick bird's eye view of what everything looks like here. Just very impressed with this microscope here, and definitely an invaluable tool when doing this kind of work. So, but yeah, very, very nice. Well, guys, I'm going to end the video here. If there's any questions on the repair, please let me know. I wanted to get this video in because I just don't see these surface mount ones come through on my bench for repair that often. They're built very well, but when they do need work, it's probably need a lot more finesse with the smaller components. Thankfully, with the right tools, my eyes are not going boggly, and I can see it on the screen as well as you guys can see exactly what I'm doing to hopefully give you an idea of what kind of work is involved for repairing something like this. The through hole is about the same amount of difficulty, but maybe a little bit quicker just because it's through hole. It's a lot easier to handle versus these tiny little resistors, which are about the size of a pinhead, about a 0.5 millimeter to 1 millimeter small. And that becomes very difficult to see without a digital microscope to see what you're doing. And also very steady hands. That's another problem, that you have to have very steady hands. Thank you guys so much again for watching. I'll see you guys on the next project.